Hey guys, welcome to the third video of this video series. I hope every one of you is safe and taking necessary precautions. So in this presentation we'll be looking at the design of a pile cap. If you remember, in our last video we have looked at the design of piles. Okay, so if you remember, we had a column. Beneath the column we had 15 numbers of piles. So the diagram was somewhat like this. So this is my column, okay, and these are my piles. Now what is a pile cap? So pile cap is actually a structure just below the column which holds together all the piles. Okay, so in this case this is actually my pile cap. Now inside a pile cap we have got reinforcements at the bottom somewhat like this. So these are my longitudinal bars, and I have also got reinforcements in the lateral direction. So this should be actually circular. These are my lateral bars. So similarly I have also got reinforcements at the top. At the top these are my longitudinal bars, and I have got lateral bars at the top also. So roughly this is the arrangement of reinforcements in a pile cap. So you can see a cage is being formed by reinforcements, right? This is actually a cage. So the arrangement of pile cap is quite peculiar. You actually get a cage at the end of the pile cap. So now let us further look how to design a pile cap. So we'll start with a problem. The problem says that there is a column of 500 mm by 500 mm carrying an axial load of 2000 kilonewton. Okay, the diameter of the piles are 500 mm and the safe load of each pile is 250 kilonewton. That means each pile can carry up to a load of 250 kilonewton. The grade of concrete is considered to be M20 and the grade of steel is considered to be Fe415. So this is the overall problem. Now let us see how to solve it. Now I know that the load coming into the column is 2000 kilonewton. Now what I will do, I will consider the self weight of the pile cap as 10% of the load coming into the column. So 10% of the load will be 10% of 2000, so that will be 200 kilonewton. So the total load which the pile cap will be facing is 2200 kilonewton. And I also know that the load carrying capacity of each pile is given to me as 250 kilonewton. Okay, so if I divide 2200 by 250 kilonewton, I will be getting the number of piles required below the column, right? So if I solve this, I will be getting 8.8. So obviously you cannot provide 8.8 numbers of piles. I will be providing something higher than this. So I will be giving 9 numbers of piles beneath the column. So this is the arrangement of piles beneath the column. There are 9 piles. So the overall shape that I will be getting is a square shape, right? Now this red color square box is actually the column. Okay, now interestingly the size of the column is 500 by 500 millimeter and the diameter of the pile is also 500 millimeter. So the column exactly coincides with the pile, but this may not be the case in every problem. Sometimes the column may be larger than the pile. Okay, so you need to act accordingly. Anyway, we have learned that the minimum spacing between two piles is 3 times the diameter. So in this case the diameter of each pile is 500 millimeters, so the minimum spacing between two piles will be 3 into 500, that is, it will be 1500. So from this pile to this pile the distance is 1500. Similarly from this pile to the other pile it will be 1500. Now look carefully. From the edge of the pile to the edge of the pile cap, this distance is actually known as overhanging distance. Okay, and the minimum overhanging distance as per IS code is 150 millimeters. So you can see I have written that the minimum overhanging distance is 150 millimeters. So this is applicable to both the sides. On the right hand side I have got 150, similarly on the left hand side also I have got 150 millimeters. So now if you add all the lengths, you will be getting the total length coming out to be 3800 millimeters. Okay, so since this is a square pile cap, so both the dimensions will be same. So on the Y side also I have got the dimension to be 3800 millimeters. Alright, now the design of a pile cap is quite similar to the design of isolated footing, which we have learned in our college. So just like isolated footing, we have got the first step, which is check for bending moment. Alright, now you know that in a footing we check the bending moment at the face of the column, right? So here I have taken a section AA just at the face of the column. Now if you look to the left hand side of this section, what do I have? If I look at the left side means this part. At the left hand side I have got 3 piles, right? These are my 3 piles. So the load carried by each pile will be 250 kilonewton, right? So all total I have got 3 into 250 kilonewton, that is I have got 750 kilonewton of load acting on the left hand side of my section AA. So 750 kilonewton multiplied by this distance will be giving me the bending moment at the section AA. Okay, so that is what I have written, that maximum bending moment occurs at the face of the column. So maximum bending moment will be 3 into 250 multiplied by the distance, which is 1.5 minus 0.25. So how did I obtain this distance? You see, from the center of this center line to the center of the middle, it is 1.5, right? And this distance is actually half the diameter of the pile. So half the diameter of the pile will be 0.25. So 1.5 minus 0.25 will give you the distance from this part to this part. Okay, so if you see the maximum bending moment, you will be getting as 937.5 kilonewton meter. So just like the footing, we can obtain the effective depth by using the formula mu equal to 0.138 FCK BD square, from which D will be equal to root over mu by 0.138 by FCK into B. So mu is the ultimate moment. So for ultimate moment I use factor of safety of 1.5 and I multiply it with 10 to the power 6 so that my moment is in Newton millimeter. At the bottom I have got 0.138, FCK is 20 and the width of the pile cap is 3800, right? This is the width, so it is 3800. So if I solve this, I will be getting the effective depth as 366.17 millimeter. Now what I do, I adopt the overall depth as 1000 millimeter so that I am on the safer side. So if I adopt overall depth as 1000 millimeter, effective depth will be 1000 minus clear cover, which is 50 millimeter, minus half of the dia of the reinforcement. So I am assuming 12 mm dia reinforcement bar, so it will be 12 by 2. So if I solve this, I will be getting effective depth as 944 millimeter. Alright, so the next step is to check for punching shear. So it's very similar to the isolated footing. What we do, we take an overall section at a distance of d by 2 from the face of the column. So d by 2 means half of the effective depth of the pile cap. So in our case, d by 2 will be 944 divided by 2, which will give you 472. Alright, so this distance is actually 472, and similarly this distance will also be 472. So if you see, if I need to know this overall distance from here to here, it will be 472 plus 500. 500 is the size of the column, right? So 472 plus 500 plus 472. So this will give you the total length as 1444. So since this section is actually a square section, so this side also it will be 1444, and the depth will be effective depth, which is 944 millimeter. So this is very much similar to the isolated footing. So if I now want to calculate the area available for punching shear, I have got 144 into 944. Okay, so this is the area of one side. So I have got 4 sides, so if I multiply this area with 4, I get the overall area available for punching shear. Now let us see what is the punching shear stress acting at the pile cap. So I have got a load of 2000 kilonewton, which is the axial load coming into the column, and I multiply it with factor of safety 1.5, and then I multiply it with 10 to the power 3, so that my load is in Newton. Okay, and at the bottom I have got the area resisting the punching shear. Okay, so if I solve this, I will be getting the punching shear stress acting on the pile cap as 0.55 Newton per mm square. So this is actually the punching shear stress that is acting on the pile cap. Now let us see how much the pile cap can actually resist. Okay, so this is we have done in our isolated footing case also, that the punching shear stress that a footing or that a pile cap can resist is given by Ks into tau c. So Ks value, if you solve, you will be getting it as 1, and tau c is 0.25 into root over fck. Fck in our case is 20. So if you solve this overall equation, you will be getting the value as 1.11 Newton per mm square. So it means that the pile cap can resist a punching shear stress of 1.11 Newton per millimeter square, whereas the punching shear stress that is being acting actually is 0.55 Newton per mm square, which is actually less than the resisting shear stress. So this way the pile cap is safe when it comes to punching shear. Alright, so the next step is to check for one-way shear. Now if you remember, in a one-way shear we take a section at a distance of d, that is effective depth, from the face of the column. So exactly we have taken a section BB from the face of the column at a distance of d. So this distance is actually d, or effective depth. Now if you look to the left hand side of this section BB, what I will see is I will be having 3 numbers of piles, right? These are the 3 piles. So if I want to calculate the shear force acting at BB from left hand side, it will be because of the loads coming into these 3 piles, right? So what is the load coming in all these 3 piles? It will be 3 into 250 kilonewton. Okay, so that is what I have written over here, that at a distance of 944 mm from the face of the column, the shear force that will be acting at the section will be 3 into 250 kilonewton, that is, it will be 750 kilonewton. So this is the shear force acting on section BB. Now let us look what will be the shear stress. Okay, so shear stress acting is denoted by tau v. So how to calculate it? It will be shear force divided by the area, right? So shear force is 750 kilonewton, and I apply the factor of safety 1.5 and 10 to the power 3, so that it is in Newton. And what will be the area? Area will be 3800, because the section that I have considered is from here to here, right? So the distance or the width is 3800, and the depth will be equal to the effective depth, that is 944 millimeter. So this will be giving me the area which is resisting the shear force. So if you solve this, you will be getting the value as 0.31 Newton per mm square. Now we all know that for a section or for a structure to be safe from shear force, tau c should be always greater than tau v, right? So we adopt a value of tau c from IS 456 table 19 such that it is slightly higher than tau v. So we got that tau v value was 0.31, so let us take a value slightly higher than 0.31, say 0.36, right? So this is something we have adopted from table 19. Now from the same table you will find that for tau c equal to 0.36, the percentage of steel that is required is 0.25%. Okay, so this is the requirement of steel as per shear force. Now let us look at the requirement of steel as per bending moment. Okay, so now let us look at the requirement of steel as per bending moment. Okay, so for this we will be taking the help of SP16. Now you know, for SP16 we need to know the value of mu by bd square, where mu is the ultimate bending moment. Okay, so at the top I have calculated the ultimate bending moment, and at the bottom I have got b into d square. So b is the width, that is 3800, and d is the effective depth, which is 944. So I get the value as 0.4 Newton per mm square. Now if I look at table number 2 of SP16, I can actually know the percentage of steel. Now in our classes we have seen how to determine percentage of steel from SP16 using charts. Okay, but there is another way, that is by using tables also you can determine the percentage of steel required in your section. Okay, so this is actually table number 2 of SP16. On the left hand side you can see I have got the values of Fy. The values of Fy range from 240 to 500. So our Fy value is 415 and the FCQ value is given to be 20. Okay, so this table is exactly the one which we need. Alright, now if you look into the table, we have got the values of mu by bd square. So these are all mu by bd square, and here I have got the values of Fy. So this is for 240, Fy 240, Fy 250, Fy 415. So now the value of mu by bd square in our case was 0.41. Okay, so you can see that here I have got 0.40 and here it is 0.45. So in between I will be having the value of 0.41. So for 0.40, the percentage of steel that is required for Fe415 is this 0.114. Okay, and for 0.45, the percentage of steel that is required is this 0.128. So our value will be in between these two values. So if you interpolate, you can get value, and the value will be turning out to be 0.117%. Okay, now this value is actually less than the one which we got in shear. In shear force, or in one way shear force, we got that the percentage of steel that is required is 0.25%. Okay, and for bending moment we see that the percentage of steel that is required is 0.117. So obviously, to be on the safe side, we will be taking the higher value. We will be taking 0.25% as the percentage of steel required in the pile cap. So from the percentage of steel you can determine the area of the steel, right? So area of the steel will be percentage of steel multiplied by the area, cross-sectional area, that is resisting shear force. So the cross-sectional area that is resisting shear force was 3800 into 944. You can look at the previous slides. Okay, so this will give you a value of 8968 millimeter square. So this is the value of AST, the area of steel that is required for my pile cap. So you can see I can calculate the number of bars that is required. So 8968 divided by pi by 4 into 12 square will give you the number of reinforcement required at the bottom. So I need 79.29. that means I need 80 numbers of 12 mm bars at the bottom. Okay, so if you remember the diagram of pile cap, it was something like this. Okay, I had got the longitudinal bars and I also had the lateral bars. So now we have got that we need 80 numbers of 12 mm bars. So this you can provide it for the longitudinal bars as well as for the lateral bars also. So hence I have written that provide 80 numbers of 12 bars spaced equally along both the sides. When I say both the sides, I mean longitudinally as well as laterally. Now this you can also provide for the top reinforcement layer also. At the top also I will be having reinforcement in the longitudinal direction as well as in the lateral direction. So you can provide the same reinforcement at the top also. Okay, so this is how we design a pile cap. Now I will be leaving a small homework for you guys. You need to draw the diagram of the pile cap with the reinforcements after this problem. Okay, so this is a small homework I am assigning you. So that's all for today. See you in the next video. Thank you.